Hello. In this video, we're going to look at how to evaluate the stability of a system using a practical example. So I have drawn the block diagram for a three-stage op-amp. It's a pretty common block diagram. There's typically a diff-amp input stage, a gain stage, which in this case I've drawn as a common emitter. And then sometimes if you have to drive a resistive load, you'll have also an output stage, which could be a common collector amplifier. I've also annotated the input and output resistances of each stage. So for the first stage, I'll have a gain of negative 1000, input resistance of 10 mega ohms, output resistance of 10 kilo ohms. For my common emitter stage, I have a gain of negative 10, input resistance of 200 kilo ohms, output resistance of 10 kilo ohms. And for my common collector stage, my gain will be approximately 1, input resistance of 1 mega ohm, output resistance of 100 ohms. Now we know that even though op-amps are typically DC coupled amplifiers, they're going to have a frequency response which doesn't have a low cutoff frequency, meaning they also amplify DC signals, but the frequency rolls off, the frequency response will roll off at high frequencies due to those internal capacitances of the transistors, parasitic capacitances, and any load capacitances. Since we have a three-stage amplifier, it's reasonable to assume we're going to have 3 poles. One of them will be at the interface between the first 2 stages due to some capacitance, which I'm going to lump all the capacitors into an equivalent capacitance CP1 for my number 1 node. And there will be another pole associated with the second interface, which I'm going to label CP2 for my node 2. Now, there's typically going to be a third pole, but if my output stage is a common collector stage or another wideband amplifier, then the third pole is going to be far out enough in frequency or at a sufficiently high frequency that I can, for practical purposes, ignore the effect of that pole. So I'm going to be determining a stability based on the first 2 poles, because remember, the first pole is the one that's going to take me my phase shift from 0 degrees to negative 90, and the second pole is going to take it from negative 90 to negative 180. And that's my limit for stability, if you will. And so I care about the location of those poles. The third pole, if it is at a sufficiently high frequency, is not going to interfere. And so I'm going to make a little note here stating basically that. So assume third pole P3 is at a sufficiently high frequency that can be neglected for stability calculations. So let's see reasonable values for my capacitances at nodes 1 and 2, CP1 and CP2, could be, for example, 50 over pi picofarads for CP1 and maybe 5 over pi picofarads for CP2. The reason why I've made CP1 about 10 times larger is because we have a common emitter amplifier with a gain of 10, and if you remember, there was that base to collector capacitance that got multiplied by the gain due to the Miller effect. And so it's reasonable to assume that the pole due to the capacitance sitting at node number 1 is going to be the dominant pole of the 2. Let's take a look at how we will evaluate the stability of this system. In order to evaluate the stability, remember, we're going to need to look at the system's frequency response and then determine what's the amount of gain margin and phase margin. At the limit of stability, I want that by the time my phase shift reaches 180 degrees, my gain will be equal to or less than 0 dBs. If I have it at 0 dBs, then the system is marginally stable, but in all reality, I don't want to be too close to that limit because any disturbance in the system may cause the system to go unstable and oscillate. And so I want to have sufficient gain margin and phase margin to ensure stability. Let's take a look at how much I will have in this particular case. So the first step is going to be determining the system gain. And so since I have a multi-stage amplifier comprised of 3 stages, my overall gain is going to be approximately equal to the product of the 3 gains times any loading factors. But notice that I have made the relationships between my R out from one stage and the R in for the following stage. The relationship is such that the loading factors will be very close to 1. In other words, the input resistance of a subsequent stage is much larger than the output resistance of the previous stage. We can see that, for example, at node 1, where R out of stage 1 is 10 kilo ohms, R in of stage 2 is 200 kilo ohms, so 20 times larger. And the same thing happens at interface 2, where R out for the common emitter stage is 10 kilo ohms, and R in for the following stage is 1 mega ohm. So the amount of loading is going to be negligible in this case. And so the product of the 3 is going to be minus 10 to the 3 times negative 10 times 1, approximately 10 to the 4, or 10,000 volts per volt. I can convert that to dBs by taking 20 times the log base 10 of that amount, and I get 80 dBs of gain. And again, I'm going to make a note that I have ignored loading factors between stages, since R out of n plus 1 is much greater than R in of n. Okay. Now, if we wanted to take into account loading effects, we could do that by recalculating the gain of our amplifier, basically multiplying the appropriate loading factors, or we could have taken that loading into account when we calculated the gain of our amplifier. So basically, let's say when we come up with a gain for the common emitter amplifier of negative 10, that may have already taken into account the loading effect, and that will be the gain of the loaded amplifier based on what we expect for the output resistance of stage 1 and the input resistance of stage 3. Anyway, step number 2, once we know the system gain, is going to be finding the locations of the poles. All right, and so each pole is going to generate a low-pass frequency, low-pass response on our frequency response, which is going to be determined by the equation 1 over 2 pi R times C. For the pole introduced by the capacitance in node 1, this is going to be R1, C1, where R1 is the equivalent resistance connected to that node, and C1 is the equivalent capacitance connected to that node. And so in this case, the equivalent resistance connected to the node is going to be the output resistance of stage 1 and the input resistance of stage 2, both of them going to ground, so in parallel. And so I'll have R out 1 in parallel with R in 2, and my capacitance value is going to be CP1. And therefore, this is 1 over 2 pi. And so I'll have 10K in parallel with 200K. I'm going to approximate that as 10K. And then CP1 is 50 divided by pi pico. So that gives me my first pole location at 1 megahertz. My second pole, I will follow a similar approach to calculate its location, except in this case it's going to be 1 over 2 pi R2 C2, R2 being the equivalent resistance connected to node 2, C2 being the equivalent capacitance connected to node 2. So this will be 1 over 2 pi R out of stage 2 in parallel with R in of stage 3, CP2, and 1 over 2 pi, and the R out of stage 2 is 10 kilo ohms, R in of stage 3 is 1 mega ohm, so I'm going to approximate the parallel combination as being 10 kilo ohms times 5 over pi pico. And so that's going to be sitting at 10 megahertz. Step number 3 is I'm going to draw my Bode plot, because that's going to allow me to easily graphically analyze whether the system is stable or not. So draw my Bode plot, and it has two components that I need to keep into account: the magnitude response, or the magnitude Bode plot, and the phase response, or the phase Bode plot. And so in one case, this will be my magnitude. So this will be my A in dBs. And this will be my phase in degrees. And so I'm going to start counting at a frequency of 100, 1K, 10K. Remember, this is a logarithmic scale. 100K. Maybe that's a little bit too crowded. Let's expand it a little bit more so it doesn't get too crowded when we're actually drawing this. So I'm going to put 100 here, 1K, 10K, 100K, 1 meg, 10 meg, 100 meg. And similar tick points for the phase. Okay, and now I can put my Y tick marks. My maximum value is going to be 80 dBs. So between 80 and 0, I'm going to have 40 dBs, 60, and 20. And down here, I'm going to go all the way to negative 180 degrees. Midpoint is going to be negative 90, negative 45, and negative 135. All right, so let's get started. I'm going to draw my Bode plot for the uncompensated system in blue. So I have my DC gain, or my gain before the location of the first pole, is going to be approximately equal to 80 dBs. And so I'm going to start right here. And that's going to stay like that up to the location of my first pole, which is at 1 megahertz. So right around here. This will be my P1. And then using my Bode plot analysis, I know that my gain is going to decrease at the rate of 20 dBs per decade, or negative 20 dBs per decade after that, until it reaches the location of the second pole. So it's going to go from 80 dB to roughly 60 dB. Here is my P2. And then after that, it's going to keep decreasing at the rate of negative 40 dBs per decade. And so 1 decade later, I'm going to be at 20 dBs. And then at 1000 meg, which will be the next tick, I'm going to be at negative 20 dBs and so forth. So basically, this is a rate of minus 20 dBs per decade, and this is a rate of minus 40 dBs per decade. And for my phase, the phase is going to be relatively approximately constant and equal to 0 up until about 1/10 of the frequency of the first pole. Then it's going to decrease to negative 45 degrees by the time I reach my first pole. Maybe. So let me just draw it. It's going to be approximately steady until I reach 1/10 of my first pole, which will be 100K, and then it's going to start decreasing at the rate of negative 45 degrees per decade until I reach the location of P1, and then it will continue to decrease at the rate of negative 45 degrees per decade until 10 times that frequency, and then flatten out at negative 90 degrees. But notice that P1 is also the location of 1/10 the frequency of P2. So I also get the effect of the phase shift due to P2 starting at that 1 megahertz. And so when I add the effect of the minus 45 degrees per decade due to pole 1 plus the minus 45 degrees per decade due to pole 2, I get between 1 meg and 10 meg a rate of minus 90 degrees per decade. And so pole 2 lands at negative 135. And then the effect of P1 disappears or becomes negligible after 10 times the frequency of P1, but the effect of P2 is still there until approximately 10 times the frequency of P2. And then it will flatten out after 100 meg. So this will be, again, negative 45 degrees per decade. This is a rate of negative 90 degrees per decade. And this is a rate of negative 45 degrees per decade. Important points to note are the point where the frequency at which we reach the 180 degree phase shift, which is right here. So this will be the frequency of interest, 100 meg. That's when I reach my 180 degrees phase shift. And I can see that at that frequency, my gain is not below 0 dBs. In fact, it is positive. It is 20 dBs positive. So I still have some gain that is greater than 1. 1 will correspond to 0 dBs at the time when I reach 180 degrees phase shift. Therefore, my system is unstable. Okay. Let's make a note here and say when the phase reaches 180 degrees, my magnitude of my gain in dBs is greater than 0. Therefore, system is unstable. Now, if I wanted to determine my gain margin, I will need to look at what will be the value of my gain by the time I reach 0 dBs, and I can see that it is positive 20 dBs, and so my gain margin, if you will, is going to be negative 20 dBs. But a negative gain margin is no good, so it's less than 0, therefore that's bad. My phase margin is going to be my phase shift, or the difference between 180 degrees and my phase shift when my gain reaches 0 dBs. And since this is going to approximately flatten out at 180 degrees, I will have that 180 degrees minus 180 degrees is equal to 0, so my phase margin is equal to 0. And again, the force system is unstable. Now I can try to make this system stable by changing the shape of the frequency response. That's what we term frequency compensation. There are different methods for applying frequency compensation. There's the method of adding a dominant pole. There is the method of adding a zero, and there is the method of shifting the dominant pole. That is the method that we know as Miller compensation or dominant pole compensation. Now one can see why that would be the case. If I were to add a dominant pole, let's say if I were to add a third pole at the location of 10K, for example, maybe I'll put that in red for my compensation, right? Then I will cause my roll-off of the gain to start earlier, and therefore by the time I reach the minus 180 degrees phase shift, my gain is going to be lower. And so that's, I'm basically increasing the stability of my system. By adding a zero, notice that a zero is going to cause, just as a pole causes the gain to start decreasing at a rate of approximately minus 20 degrees per decade. If I add a zero, I will basically counteract that effect, flatten my gain, but also I will change my phase shift. And so I will basically have the effect of keeping my phase shift at less than 180 degrees for longer. In the case of shifting the pole, it's a preferred method in most cases, and the reason for that is because I'm not introducing a new pole, I'm not introducing new capacitors, but rather changing the value of capacitance CP1, so that I'm essentially shifting P1 in that direction. Okay, and so that's the method that we're going to see in the next video. For now, it suffices it to say that, we can make the system stable by changing the frequency response. And the process of generally changing the frequency response to achieve stability, that's just generically termed frequency compensation. And again, that's what we're going to see in the next video. Thank you.